Hello guys, welcome to the journey. Today we are going to learn about one of the simplest sorting algorithms, that is bubble sort. In this video, we will break it down step by step and implement in Java. By the end of this video, you will have a clear understanding of how the bubble sort works and when to use it. Now let's talk about what is bubble sort. Bubble sort is a simple sorting algorithm that repeatedly compares adjacent elements and swaps them if they are in the wrong order. The largest elements bubble to the top, similar to the bubbles in the water. Now let's break down the algorithm. What are the steps involved in the process of bubble sort? First step, start from the first element and compare it with the next one. If it is greater, swap them. If it is not greater, ignore it. Then move to the next pair and repeat the process. Like if it's a greater, swap them. If it is not great, ignore it. After each full pass, that means a length of an array, the largest element is at the correct position. For each pass, we will place one element at the correct position. Repeat the process for the remaining elements until sorted. That means it will run the multiple times, same as the length of the array. For example, if there are 10 items or 10 elements in the array, it will pass 10 times. Each time, it will place one element at correct position. Now let's go through the step by step process by taking an example array. I am taking in a 5 elements array, integer array, 5, 1, 4, 2, 8. These are not in a sorted order. In the first iteration, first pass, first we will take a first two elements as a pair. We'll compare it. In this case, 5 and 1. Since 5 is greater than 1, see, as per our steps breakdown, if the element is greater than next element, we will swap it. Once the swapping is done, we can see the resultant array 1, 5, 4, 2, 8. The first two elements has changed their position. In the next iteration, compare 5 and 4. 5 is greater than 4, so swap it. After swapping, the resultant array will be 1, 4, 5, 2, 8. Here you can see 4 and 5 are changed their places. In the next iteration, compare 5 and 2. Since 5 is greater than 2, swap it. Resultant array will be 1, 4, 2, 5, 8. Here you can observe that 5 and 2 has changed their places. When it comes to the fourth iteration, compare 5 and 8. No swap needed because 5 is less than 8. The final step, largest element A is placed at the end. That means it's in the right position. When it comes to the next iteration, see, if you observe here, we are not going to do 4 iterations as before because the last element is already in a position, so we are reducing one iteration. In this one, the resultant source array is 1, 4, 2, 5, 8. Now we are comparing 1 and 4 because 1 is less than 4, so no need of swap. We will go to the next pair. We will compare 4 and 2. Since 4 is greater than 2, swap it. The resultant array will be 1, 2, 4, 5, 8. In the third iteration, compare 4 and 5. 4 is less than 5, so no need of swap. So in the second pass, second largest element 5 is placed at the correct position. When it comes to the third pass, see here the number of iterations came to 3, from 3 to 2. Here compare 1 and 2. See, 1 is less than 2, no need of swapping. Compare 2 and 4, no swapping because 2 is less than 4. The third largest element 4 is placed at correct position. When you come to the fourth pass, compare 1 and 4. 1 and 2, no swap required because 1 is less than 2. The array is already sorted, so we stop here. The final resultant array is 1, 2, 4, 5, 8. Now let's go through the code. Whatever we have gone through the previous slides, previous steps, like what is bubble sort and what are the steps involved in the bubble sort, and how the iterations and number of passes will happen, we will implement here. We already implemented. We'll go through the code. See, the main source for this algorithm is array of integers, and we are keeping in a size of the array boolean swapped. I'll explain this swap, why we are using. We have to iterate through the array, and as I explained, see, we have to do the size, whatever the size we have to do some number of that many iterations. If you go inside that, we need to compare each element with an other element, so we are using a nested for loop. In this nested for loop, if you check this one, if array of j is greater than array of j plus 1, we are taking in a pair of two numbers. We are checking it. If the item is greater than next item, we will do swap operation. Otherwise, we won't do swap operation. See, if the swap is happening, we are setting swapped is equal to true. See, this is the one pass. If you observe inner for loop, we are every time we are reducing the size by I. For example, if it is in a 0, we are doing it. We are not reducing. We are passing all the items. If it is a 1, we are reducing a one iteration because the last element is already sorted. It's in their right position. No need to compare again that one. Like that, for every iteration, the size of the inner for loop will reduce. This is how we are performing, and we are taking an example as 64 30 34 25 12 22 11 90. In the first iteration, 64 32 34 will be compared. It is greater than 34. First element is greater than 34 second element, so we will swap it. And we can say we are calling in a bubble sort, we are passing an array, and we are going to print it. Here, the reason for using a swapped as a flag, see, for example, in one iteration, if there are no swaps happened, that means all the elements are in the right position. So we are not if it is not swapping is if is swapping is not happening, we are not going to set as a true. Here we are using an if statement. If it's swapped is equal to false, we will break it. That means the items already in the swap position, no need to go for the next iteration, so that we can complete this sorting in order of n. We will go through the complexity time complexity of about the bubble sort algorithm in the next slide. Right now I'm just giving a clarification like how it is going to be affected. We are using the swapped flag. Now let's talk about the time complexity. We will analyze the performance or complexity of the algorithm based on three stages: best case, worst case, and average case. If it is a best in this algorithm, if it is a best case, that means the algorithm is already sorted, no need of swappings. So there will be no need of another iteration, only one iteration. If you remember that in the code, we are using an inner loop and we are setting a swapped is equal to true. If it is true means swapping is happening. If it is not true, if it is false means swapping is not happened. So means in one iteration only we will get to know that the array is already sorted. So no need of any further sorting. So order of n, we are just passing one time the size of the array, that is n. Worst case, for example, if you take the array is sorted in descending order, we were checking for the ascending order. That means it's completely opposite. That means reverse. So we need to swap every item. We have to go through all the passes. So it will take n into n, outer for loop and inner for loop, n into n. That means n square. It's a worst case. Average case, for example, some items are sorted, some items are not sorted. It's a randomly sorted. So there is no other way. We have to go through all the iterations, both outer for loop and inner for loop. So it will take an n square. Let's see the comparison between the other algorithms. What is the efficiency of this bubble sort algorithm? Now let's compare the efficiency and complexity of the bubble sort algorithm with merge sort and quick sort. We will see this merge sort and quick sort in further videos. We'll just concentrate on the bubble sort right now. Just to make it how efficient this algorithm is, I'm just comparing between the other algorithms like merge sort and quick sort. See, bubble sort, the best case time complexity is order of n. As I explained, if it is already sorted, no need to sort again. Average case time complexity means if it is items are randomly distributed, we have to do. There is no other way. We have to go through all the process of iterations. Worst case time complexity means if we wanna sort it in ascending order, but the given input array is like a descending order, so we have to keep sorting all the items. When it comes to the space complexity, there is no need of extra space. We will use the same arrays of size and space. We will do the same operations all within that array only. When it comes to the stability, see, relative order of the equal elements, it won't change. It will keep the position of the relative order of the equal elements. No need to worry about that. And if it comes to the use case, if it is useful for the small data sets and just to learn about how the comparison sorting will work, we can use this bubble sort. If we take a merge sort and quick sort, we can see that merge sort will take in a best case order of n log n, average case is an order of n log n, worst case is order of n log n. Here, if you compare average case and worst case, it is much better than n square. So we will discuss about this merge sort in future videos. Don't worry about the implementation of the things. I'll explain further. And when it takes to the quick sort, Quicksort is also same order of n log n. In worst case scenario, it will take an n square. Very rare cases. When it comes to the space complexity, for quicksort it is not required, but when it comes to the bubble sort, it required an extra space because we are using an divide and conquer approach. When it comes to the stability, merge sort have a very good stable. It's a very stable algorithm. Quicksort is not stable at most of the times. When it comes to the merge sort, we'll use for the larger data sets and linked list. We will discuss this linked list in the future. When it comes to the quick sort, general purpose, efficient in most cases. Only drawback is like a stability. When it comes to the optimization, early exit condition. For example, if you remember that in a code, we are setting a flag like in a swap. If it is swapped, then we will go to the next iteration, or else we will ignore the next iteration. That's why we are using a no swap occurs means break early. No need to worry about the next iteration. It is already in the sorted. Avoid unnecessary comparisons. Reduce the range of comparisons in each pass. For example, if you remember that inner loop, we are going to I in the for loop, I is less than n minus I minus 1. Every iteration we are reducing the one position, one item's position, because the last item is already in the right position. This is how we can reduce one iteration in every pass so that we can reduce the burden. These the two kinds of techniques we can use it to optimize the comparisons. When to use bubble sort? For example, when the array is small, for example 10 items, 20 items or something, we can easily adopt this bubble sort because there is a n square means if it is just 10 items, n square means 100 iterations will happen. Max 100 iterations will happen. If it is 1000 items or 100 items, it will take lots of time. So it is not suitable for the larger data set. Next case, for example, it is an almost sorted. For example, if you want to make sure that either the elements, given elements are sorted or not, we can use this algorithm. It will execute in order of n. For example, if all the elements are sorted, no need to no swap occurs. So we can break the loop in the first iteration only. We can use this algorithm for the educational purposes. Great for learning sorting logic. See, we here what we are doing. See, comparing and early exiting and reducing the comparisons. These kind of techniques we can learn from this algorithm. So if it's simple, it's not efficient, but it's good to learn these kind of logics. That's why we are using a bubble sort algorithm. Let's come to the summary. We learned about bubble sort, its working mechanism, time complexity, and we have implemented in Java, and we come up with the two different strategies to optimize the algorithm. I hope you guys are enjoyed learning. Thank you guys.